Here we are given the MIPS machine code instruction expressed in hexadecimal to be converted into MIPS assembly instruction. So our partial coordinate number 1, first we multiply the last digit here by the last digit of our PID, in which mine is 8. We then continue to convert each of these 8-bit hexadecimal number into 4-bit binary. So that will give us 8 fours, 32 bits, in which we know that a MIPS register is 32 bits wide long. We then continue and select the first 6 bits starting from the most significant bit, and this would represent our up field because we know the up field in either the R format, the I format, or the J format all will have 6 bits wide long. So selecting those 6 bits, we see it's 001100, which in decimal corresponds to 12, and in hexadecimal 00C. We can see according to our testing reference sheet that the opcode 00C represents AND. And as we know from our knowledge that AND will follow the I format. As we see here in our table, the I format has the up field, the RS field, the RT field, and the immediate field, in which our case here will be a constant. We can see that the RS and RT fields both are 5 bits wide long, so we continue by selecting the next 5 bits for RS and the next 5 bits for RT. Then converting those to decimal, we can see that RS would represent 4 in decimal, and then RT would represent 10 in decimal. We then go back to our reference sheet and we could see that the number 4 will represent register A0, and then the number 10 here will represent register T2. We then convert our immediate value or constant value, which contains the rest of the bits, which is 16 bits, to decimal, which is 8, or in hexadecimal 00008. We then continue to write the assembly instruction, which takes the form of AND register T2, register A0, and our constant 8. We can see that in the I format that it's in the up RSRT and immediate format. But here in writing the assembly instruction, we could see that it's the up, the RT, then RS, and then followed by the immediate. This is because the way the circuit was designed and made that it switches when you convert from the machine code to the assembly instruction. Moving on to partial coordinate number 2, we continue with a similar idea in which we multiply the last digit by our last digit of our PID. This will be 24, or in hexadecimal 18. However, this will give us 9-bit hexadecimal, but we want to continue with 8 bits, so we remove one of the zeros. We then continue as normal by converting each of these 8 bits to 4-bit binary. We then select our 6 bits, which is our upfield, and then convert it to decimal. We could see that's 4, and then into hexadecimal 004. We could see that 004 represents BEQ, which is our branching instruction. We then select our next 5 bits, which will represent the RS field, and then the next 5 bits for the RT field, because we know that the branching instruction also follows an I format. We can see that RS represents 10, and as we see in partial coordinate number 1, that represents register T2. We see RT is all 0, so that will be register 0, and the remaining 16 bits, which is our constant value, which would be 24 or 00018 in hexadecimal number. We write our assembly instruction in which the branching instruction follows the I format of up RS RT, which will be BEQ, our branching instruction, register T2 and register 0, and our constant 24 or 0018. Thank you.